So, we name this as equation 1, and to remind you that we have this factor which is 1 divided by root over of n factorial, and then there is a product of n lambda factorial, and lambda really goes from 0 to infinity. So, this is our normalization factor, and these normalization factor normalizes the many body wave function psi, which is written in equation 1, the left hand side of equation 1, and this quantity which is p to the power 1 minus s g n k divided by 2, it symmetrizes the wave function. So, what we mean by symmetrizing the wave function is that as has been told earlier, that for the fermions any change in the position of the particle or transposition of two particles would bring in a negative sign, and if that is done twice, then it brings back another negative sign, which means it becomes positive, whereas for bosons it is always positive, no matter how many times the transposition is done. So, this is our many body wave function that we are going to talk about. Now, let us look at a typical many particle state as this. So, we are giving an example of a many particle states. Let us say that it is written with a kate which is 1 1 1 1 and then 2 2 and then 3 3 3 and then it is 4 and then it is 6 6 and etcetera. So, what is meant by this notation is that at the real space, that is I equal to 1 as the position space, for I equal to 1 there is one particle, for I equal to 2 there is another one particle, then at I equal to 3 then there is another one particle, I equal to 4 1 particle, I equal to 5 2 particles, so I equal to 6 2 particles and so on. Now, this notation for a many particle system can be simplified if we simply write this as 4 and then 2 and then 3 and then 1 and 0 and 2 and so on. So, in going from this many particle state on the top from in the written in the position basis, we have gone to a many particle state where we have simply written down the number of particles that is at position. So, these are there are 4 number of particles at the first 4 positions, rather. So, there are 4 occupancy in the first 4 sites or locations, and then it is 2, then there are 3 and 4 1 and there is no 5. So, if we put a 0 and then there are 2 6 and so on. So, now this is written in a basis which is called as the Fock basis. So, what is a Fock basis? So, we have written down this many particle state or the wave function in so telling that how many particles occupy. So, occupy position I. So, for fermions, of course, we know by the exclusion principle, Pauli's exclusion principle. So, the numbers will take values, the numbers that is written here, the numbers will take values 0 and 1, and for bosons they can be any. Because bosons do not have any exclusion principle embedded there. So, as many as possible or as many as number of particles are there, they can occupy the same energy level unless it has been or rather constrained by any other principle or any other symmetry argument. Now, this writing it in the occupation basis or the particle number basis is called as the Fogg basis, and we will call this as a occupation representation. And this is same as the Fogg basis or Fogg representation, and this is after the name of Russian scientist, V. A. Fogg. So, now we will write this Fogg basis as, so this is written with a curly f, like this, and so the many body state would be written as in this occupation number is this. I am writing it with a ket, we could have written this with a ket as well. So, this is equal to some n 1, n 2 and so on, and then there is a n, and this C n 1, n 2 and all of that, and then it is n 1, n 2 and so on. So, that is the many body state where C, n 1, n 2 etcetera are the coefficients, and these are the Fogg basis. So, the occupation number basis. So, we have occupation n 1 at a given site, and then occupation n 2 and occupation n 3 and so on. N 1 and n 2 will all be equal to either 0 or 1 for fermions, whereas for bosons they could be any number. Now, in general we have n I equal to n. So, the total number of particles is equal to n. However, in a grand canonical sense we can relax this constraint, and we can say that we have a Hilbert space which is large enough to accommodate infinite number of particles. So, then the total Fogg space is written as Fogg space is written as it is equal to a notation that I will use, I will just tell in a while. It is n equal to 0 to infinity, and this is equal to the power n, where this is known as the direct sum. Now, this Hilbert space must necessarily include F 0, which is vacuum, means that it does not contain any particle, and it necessarily should be to include in the family of basis states. So, now we have a state which is given by this and written in the occupation basis or the fog basis, and in the fog basis the total fog space is written in terms of the this f to the power n and written as a direct sum from n equal to 0 to infinity, and we do not have this constraint of this one any longer, that is sum over n I, which is basically the occupancy of each state has to be equal to some finite number n, that is not there any longer. So, what is this occupation number representation useful for? So, what is the benefit derived from starting from a representation which we have written in the position basis, and then we have tried to go on to the occupation number basis or the fog basis? What is the benefit of doing that? In fact, it of course, as you can see that this looks much more simpler as compared to the representations that has been used earlier, that is the position representation. However, in the position representation there is an enormous summation involved here in equation 1, which is a sum over k, and then there is a p to the power 1 minus s g n k by 2. It has been told earlier and it is written here as well that s g n k is either equal to k plus 1 or minus 1, and when it is equal to plus 1, then there is no sign, that is this factor is equal to 1. However, when there is a s g n k is equal to minus 1, then we have sign. So, that becomes p equal to 1, where p is equal to plus 1 for bosons and p equal to minus 1 for the fermions. And from there we wanted to go to this occupation number basis, and even though it looks simpler, but this enormous sum that appears here, how is it going to be taken care of? And remember that this sum is important for the symmetrization of the state, and this symmetrization gives the Slater determinant for the fermions, which is the antisymmetric property of the matrices are encoded in transposition of particles for fermions, which would pick up a negative sign as one does a transposition or changes the position of one particle. So, how that is going to be encoded into this occupation number basis, and in principle we are need to be worried, because we are talking about 10 to the power 23 number of particles, and the transposition of them leading to the right symmetrization for a particular wave function need to be taken into account. So, this is done very elegantly in the using a second quantized formalism. So, this is where the second quantization is important, and we will tell you how it is important. So, let us define a creation operator which is acting on a many particle system such as this. So, A I dagger acting on n 1, n 2 etcetera, and that by definition we are now using a definition that we are going to we are introducing it for the first time, and this is n I plus 1, and then there is a p s I, and then there is a n 1, n 2 and n I plus 1, and so what it does is that A I which is a creation operator. So, this is the definition of operation of a creation operator. So, creation operator acts on the ith particle, and raises the occupancy of the ith particle from Ni to Ni plus 1, brings in a coefficient which is root over Ni plus 1. Additionally, to take care of the symmetrization requirement, brings in another factor which is p to the power Si, and where Si is equal to summation over j from 1 to I minus 1 and Nj. So, we will have to sum over all the occupancies up to that ith site, just before the ith site, and that ith site, of course, the occupancy is raised by 1. Now, it is important to note that, so in a fermionic system, so for fermions, this Ni is modulo 2. So, what we mean by modulo 2 is that when you divide a number a by n, it is called as a modulo n, and what it means is that when you divide a by n, the answer is the remainder of this division. So, for fermions, the division will leave a number which is either 0 or 1, because I am dividing by 2. So, n is equal to 2 here, and so Ni is modulo 2 means that automatically it means that it can acquire values 0 or 1, and that is the reason, or rather that takes care of the fact that the occupancy of fermions at each site could be either 0 or 1, and so that emphasizes the Pauli's exclusion principle. Now, let us take a, so basically, so p to the power Si, it makes accommodates, or rather incorporates the symmetrization, the proper symmetrization of the many particle state. So, let us give an example. Take a many particle state which is n 1, n 2, n 3 and so on, and let us operate by a creation operator which operates on this third occupation, and then we can write this as root over of n 3 plus 1 and p to the power n 1 plus n 2, and we have n 1, n 2, n 3 plus 1 and so on. Okay. So, this is the operation of the creation operator acting on n 3. So, as usual, p takes a value, p takes plus 1 for bosons and minus 1 for fermions. Okay. And so, this PSI here n 1 plus n 2, this takes care of symmetrization of the state, which means that if n 1 plus n 2 is equal to 1, then we have an antisymmetric state, because for fermions It is an antisymmetric state because it is minus 1 whole to the power 1. However, if n 1 plus n 2 is equal to 0, then we have a symmetric state, or n 1 plus n 2 equal to 2, we have a symmetric state. And so, this is how in this fork basis the symmetrization of the many particle state is encoded, and it is very elegantly done in the second quantized formalism. You will get more glimpse of it as we go along. So, now let us then write down a wave function, a many particle wave function in the fork basis as this, which is a product of, and this is a n I factorial, and there is a a I n I acting on a vacuum. Okay. Let us call this as equation 2. And if you remember that we have insisted of having this vacuum, or that F 0 that we had written, which is a null state, or the particle without any particles, as an important element in the family of the fork basis. And this is, we actually create a many particle state by successively operating the creation operator on the vacuum. And so, this complicated permutation entanglement, which is there in equation 1 here by this summation over k and p 1 minus s g n k by 2, now that is encoded here. And how would it be encoded? It will be encoded through the commutation relation of these operators, and that is why this formalism of second quantization is so helpful for dealing with many particle systems. So, this basically tells you that there is an n-fold application of this operator A dagger on the vacuum state to build a many particle state. Okay. Let us try to understand that how the symmetrization is built in by the commutation relation of these operators. Let us take only two particles to begin with. So, we have two particles, and say they are located at A I or rather I and j, and they are, so we just write them as A I dagger and A j dagger as the creation operator for these two particles. So, as if they are acting on vacuum. So, A I dagger and A j dagger acting on vacuum gives me that state, which is what I want to consider. Let us call it just a two particle state. Okay. And let us look at the commutation relation of these two particles, and needless to say here that I is not equal to j, because for fermions it is anyway forbidden to have I equal to j. You can't have two particles being formed at the same site or being created at the same site. So, let us define the commutation relations by this A I dagger A j dagger minus p A j dagger A I dagger and equal to 0. So, what I have done is that I have written them as in I and j, and then in the next term I have written with a minus, I mean with a j and I. In addition to that, we have a minus p, and so where p is equal to where p equal to 1 will stand for denotes commutation relation, and p equal to minus 1 denotes anti-commutation relation. Let us see clearly what it means is that we have a I dagger, a j dagger, and I will write a p subscript here which is equal to 0. So, the notation is that if I have two operators a and b and written with a p as a sub with a square bracket, and this is equal to a b minus p b a. So, for commutators, this relation is p equal to 1, which is equal to a b minus b a, and for anti commutation. So, this is the commutation relation of a and b, and this is the anti commutation relation for a and b. So, if this commutator is equal to 0, then we say that this two operators commute, and when two operators commute, it is usually correct that they have same set of eigenfunctions, they have common eigenfunctions, and if they do not commute, then that does not hold, and this is the anti commutation relation of. So, it is the anti commutation relation. Okay. And if we go back to our a I dagger, a I dagger, then that is equal to 0, because the identical operators would commute. And so, if we summarize here these relations, for all I and j, a I dagger, a j dagger equal to p equal to 0. So, so similarly, we have we can write this as so for both p equal to 1 and p equal to minus 1, and just like the similarly, if we want to write it for the annihilation operator, just like that a creation operator takes n component Fock state from this to this f n to f n plus 1, we can also talk about annihilation operators. Which will take my Fock state n to n minus 1, and we have relationships, similar relationships, commutation relationships for the annihilation operators as well, and they are written in a compact form by this relation, which is equal to this and a I a j p equal to 0 and a I dagger a j dagger p equal to 0. So, the enormous complexity of the many particle space and the complexity that is related to symmetrization of the many particle wave function is taken care of in the Fock basis by choosing, or rather from the commutation relations or the anti commutation relationships of the operator, and this is a phenomenal improvement of the situation, as we can see in our next discussion.